Okay. Okay. So I think it's about time to get started. Hi, I'm Matei, and I'm going to talk about cloud computing, MapReduce, and Hadoop. So cloud computing is sort of a buzzword these days. MapReduce is a programming model for the cloud that's very popular and actually pretty simple to use. And Hadoop is the open source implementation of MapReduce that most people that use MapReduce are using. So I'm a grad student here at Berkeley starting my 4th year in computer science, and I'm also a committer on the open source Hadoop project. So I'm going to tell you a little bit about it. So let's start a little bit with cloud computing. What is it? So the answer is that there isn't really a great definition out there. It's just a great buzzword if you're a startup or a business to say that you're doing. But okay, here's how I think about it. So when people talk about the cloud, they just mean these large internet data centers that most big internet properties run on, including Google, Yahoo, a lot of Microsoft stuff, Facebook, and so on. When people talk about cloud computing, though, they refer to this sort of new class of services where you, as a customer, can rent computing cycles on these clusters. So the prime example of cloud computing, the most famous one, is Amazon's Elastic Compute Cloud, or EC2. And this is a service from Amazon where you sign up with your credit card and you can get these virtual machines running Linux or whatever. And the prices are pretty low. They're 8.5 cents an hour for the smallest type of VM. And more interestingly, it's billed by the hour. So you can get some machines, use them for a few hours, toss them away, and you've paid a few dollars out of your pocket, but you could have run some interesting parallel jobs on those machines. Amazon S3 comes with that. It's a storage service where you can keep data in the cloud. And why are people interested in this? There are a few nice features that this model offers. One of them is the scale that you can get. So you can sign up on these services and rent 100 virtual machines, or even more than that, if you want, which may be very hard to get by yourself as a researcher or a grad student or whatever. And the other interesting thing is this hourly billing. So once you're done with the machines, you can just throw them away. You don't need to buy 100 machines and think about what am I going to do all year with these. How will I justify getting these, and so on. So it's really nice that way. And the last thing is the ease of use compared to even owning your own machines. You just need a credit card to sign up. You actually fully control the machines. You get root access. You can install whatever you want on them. If you break one of them, you can just toss it away and get a new one. So these are the nice things about it. Now, what is MapReduce? So MapReduce is a parallel programming model for these data center environments that's really designed to work well in these environments. And it started out as Google. It's used for a lot of things at Google. Many of the large-scale batch processing they do is on MapReduce. And they said that they process 20 petabytes of data per day using it. This was a few years ago, so it's probably more now. But it really took off thanks to this open source project called Hadoop that started as Yahoo and is used by essentially everyone who isn't Google or Microsoft and does cloud stuff. That's the Hadoop project. So what do people use MapReduce for? There's a whole bunch of applications. These are just some examples of the things it does. So these are in industry. So as I said, a lot of what Google does, indexing the World Wide Web, clustering stuff to give you relevant articles or relevant ads or whatever, machine translation, which they're actually very good at. These are all running on top of MapReduce. Other things are finding spam, suggesting people as friends for you on Facebook, these kinds of things all happen on top of MapReduce and Hadoop. I just wanted to show one example of why people might do this, why you might do this if you're a web company. So this is a fun sort of publicly accessible app at Facebook. It's a data mining app. And it lets you see how often different phrases happen in wall posts at Facebook over time. And this is kind of a silly one. You look at party tonight and hangover, and we see, they happen on this sort of weekly cycle, which kind of makes sense. There are big parties at Halloween and New Year's. And at least here you can see people spend a bit more time talking about the hangover than the party. Okay, so this is, yeah, this is kind of silly and fun, but you know, if you were, say, a business intelligence person at Facebook or an executive making decisions, this is a more interesting one you can look at. You can look at, this is people saying hello in different languages. And you can see here sort of the Spanish takes off, the Italian takes off. This is when they started opening Facebook in those countries and marketing it and so on. But you can see the French Zaharia isn't doing that well. So maybe this means you should spend a bit more time figuring out what's going on in France. Okay. And of course, MapReduce is also interesting because people other than web companies are starting to use it, especially people with big volumes of data. And here are just some examples of more scientific uses of it that I found. A lot of these are sort of, I ran a simulation and I want to process the data, which is useful because you have all this output and you need to know what it means. Other example like bioinformatics, they're running their computation directly on MapReduce. And I think one of these simulation applications did that too. And of course, your application might be here if it's suitable for this. Okay, so what am I going to talk about? I'm going to start by talking about MapReduce, sort of the architecture, the programming model, and the design goals and what it's good at. I'll show you some examples of how you can use this programming model to do different things. And I'll show you a little bit of what these jobs might look like in Hadoop and how to get started actually implementing these with Hadoop. Then I'm going to talk about these two tools, Pig and Hive, that are sort of higher level languages built on top of Hadoop that make it easy to do these data analytics types of queries. They're basically database type software built on top of Hadoop. And finally, I'll talk a little bit about Amazon's Elastic MapReduce. This is a service from Amazon that lets you run Hadoop jobs in the cloud, and it takes care of launching a cluster for you and monitoring it and doing all that stuff. I just wanted to show you what it looks like. Okay. So let's dive into the architecture. So first of all, what are the goals of MapReduce? There are really sort of two design goals that went into the system. The first one was scalability, and especially in terms of data volumes, as opposed to, say, the amount of computation you do, which is what traditional supercomputing is about. And what's interesting about data is storage of data is very cheap, so you can probably get your new laptop or whatever will have 1 terabyte of data on it. But accessing data once you have it stored is actually pretty slow. So your disk will typically read at something like 50 megabytes a second, maybe 100 if you get a really fancy disk. And for example, say you were Google and you had this 100 terabyte web call and you wanted to do something interesting with it. Well, if you put it on one node, it would take you a very long time to just read all that data again, do anything with it. It would take you 3 weeks here. On the other hand, if you put it in a cluster and you have many disks all reading some chunk of the data in parallel, you can get the job done a lot faster. So this is really the main reason to go parallel with big data, is because otherwise you're just not going to get it out of the storage in time to do anything interesting with it. The second goal, which is also kind of interesting, is that MapReduce is really designed to be cheap. It's not designed for sort of the best sort of ultimate throughput you can have. It's sort of for throughput per dollar. And this is because, of course, it came out of these industry environments where they care about margins. So how is it cheap? The main way it's cheap is by using inexpensive sort of commodity hardware. This means that they'll buy servers and things that are a few generations old, not very reliable, but that means you can get them for a low cost. They'll buy networks that are pretty cheap, just your standard Ethernet network, no fancy interconnect, and so on. And the downside of this, though, is that all these cheap components will fail. So the main trick in MapReduce to deal with that is this automatic fault tolerance that it does. And fault tolerance in the system is nice because if you didn't have it, you'd have to go around fixing stuff every time it fails, and that's expensive. It requires a person to run around and do this. And the last thing, of course, but it tries to be easy to use so that you don't need to, to be an expert to actually write a parallel job, and so you don't need to hire a lot of experts to do it. So this is all I view it as cost efficiency. Here's what a Hadoop cluster might look like. Just an example. This is actually from Facebook, which has a 2,000 node Hadoop cluster now with some of these specs. So you'll have these nodes. Each node has several disks on it. I think this one had 8 disks, yeah, and some cores and stuff. And then the nodes are grouped into racks, and this is a 1 gigabit sort of Ethernet within a rack is typical. And then these are racks in your data center, and then from the racks there may be a bigger network pipe going out to this aggregation switch in the middle. But one thing to notice about it is the network bandwidth. So actually, if you look at the bandwidth of 8 disks, how fast you can read data off them, that's already more than the size of the link coming out of this node. I think it's going to be about 2 gigabits or something. And then if you look at the size of this link up here compared to the bandwidth of those disks, it's much smaller. So what this means with the cheap network is that you have to do scheduling in such a way that you don't read data across the network when you don't have to. So the data locality matters in these systems. And that's what MapReduce tries to do for you. Here's what the cluster might actually look like in real life. This is a picture from Yahoo from one of their clusters. Okay. And so what are the challenges with running in this environment? I talked about some of these before. So we have failures. And of course, the more nodes you have, the more likely it is that something will go wrong during some period of time, like say an hour. So that's why the system has to be fault tolerant, and MapReduce is designed to do that for you. You have this commodity network, as I talked about, which means it's low bandwidth, so it means you have to place computations near the input data. And of course, just writing distributed systems in general is hard. Writing them in this environment where things are flaky and fail is even harder. So the programming model in MapReduce is designed so that you don't have to do that. You write these 2 functions called map and reduce, and the system takes care of scheduling them or figuring out what to do if some of them fail and so on. So it does that for you. Okay. Let's look at the components that go into it. So typically when you're running MapReduce or Hadoop, you'll have 2 components. One of them is a distributed file system that just stores the data across the cluster on the different disks and makes sure that it keeps it replicated and so on, so that you still have a copy of the data if some of the nodes failed. So in Hadoop, that's the Hadoop Distributed File System, or HDFS. And then you have this framework running on top, which actually you can submit jobs to as a user, and it will run the jobs. And it does the scheduling for you. And you run these on the same set of nodes, of course, because you want the computation to happen on the nodes where the data is sitting. So before I talk about MapReduce in more detail, I just wanted to say a few things about the distributed file system, just that will be useful to understand what's going on. So it's actually not a very complicated thing. Basically, the distributed file system will split files into blocks. In Hadoop, there are 128 megabytes by default. And these blocks will be replicated across nodes. And the nodes that store the data in Hadoop are called data nodes, and there's something called a name node that's sort of the master. And the name node just keeps track of which blocks are part of which file. So if file 1 has blocks 1 through 4, and it knows where each of these blocks have copies in the system. So some important things about it, though. The system is really optimized for large files. As I said, a 128 megabyte block size. That's a lot bigger than any file system you have in your desktop or whatever. And it's also optimized for sequential reads, where you're going to be just scanning the whole file. And if your workload doesn't do that, then it may not perform very well on here, especially if you have many small files. That places a lot of load on this metadata server, the name node. Another thing in Hadoop is that the files are append only, so you can't go and randomly edit stuff in the middle of the file. And again, this makes it easier to manage, makes it easier to have it fault tolerant. You don't need to worry about keeping all the replicas in sync because they never change. They never have to change. You just add data. But it's something to be aware of. And yeah, that's what I wanted to say about this. Okay, so now the MapReduce programming model itself. So as I said, there are these two functions, map and reduce, and these functions work on records, which are just elements of data in your input. And the records are just key value pairs in MapReduce. The key and value can be whatever. They can be strings, integers, things like that. So you'll write two functions. First one, the map function, takes these input keys and values from your input data. And for each record in the input data, it can output 0 or more what are called intermediate data values. That's these ones over here. So you go through and you can do something here like filtering the records or extracting parts of them that you care about, things like that. That's what map is about. Once you've done that, you want to, to probably do something with those results, and that's where the reduce function comes in. The reduce function is given each intermediate key and all the values that were produced for that key by all the maps. Given that, it can think about it, and it can output a list of output records that come out of the job. So that's how it works. I'm going to give an example next, just so you can see more concretely what it does. But feel free to ask if you have questions also. Okay. So here's one example, sort of the hello world of MapReduce, is word count. So we just we have a big file or set of files, and we want to see how often each word happens in them. So in this one, our input records are going to be lines of text, let's say, and our output, we just want for each word the number of times it happened. So in the map, what we do is we split each line of text into words, and we output these intermediate records, which are word as the key and one as the value. Then in the reduce, for each word, so for each key, we sum up all the values. So we sum up those ones, and we basically get a count of how often that word happened in the data set. So yeah, so that's just how word count looks. So here's a picture of how it will actually get executed on a file. So on the left here we have a data file, and it's split into blocks. You can see these 3 blocks over here, and each block has some lines of text in it. These go through the map, and the map outputs these intermediate records. So there's actually one map process happening for every block of the data, and these could be happening in parallel on different machines in the cluster. And of course, they also push to where the data is, preferably. So for example, in the first one, we have the, brown, fox. These are all some words that came out as intermediate records, and we also have quick. So these maps output these intermediate values, and then the values get grouped by key and sent to the reduce tasks. And there can be multiple reduce tasks for different sets of keys. So this reduce task at the top is getting sort of these words over here, and the one at the bottom is getting these other words. And the reduce tasks do the adding, and then you get an output file over here. Okay. So that's how this looks. So there's one other detail before I go into more examples. So if you look at this carefully, you'll see that there's actually some inefficiency here, because we have some maps that output the same word many times, and we just get many records with that value. For example, here the word the happened twice, and we send 2 of these records. And this means sort of more network traffic makes the job more expensive. So the other thing you can do in MapReduce is specify something called a combiner, which is like a local reduce function that happens on each node and aggregates the results of that node. So for example, for word count, we can do the same thing we did in the reduce. We can count up those ones, but do it locally on each map. And the way that looks in this job is now this map over here will have done some combining locally, and you'll only send this record, the and 2, across the network. Okay. Okay, so that's the basic model. Just a few more details that are useful to know. The system tries to schedule these map tasks on the same machines that have the input blocks of the file, and this is to avoid this expensive network communication I talked about. And it just does that automatically for you. You don't need to do it yourself. The other thing is about the status of these intermediate results. So these results that you see here don't just get sent directly to the reducer. They're also saved on disk on the machine that ran the map. And the reason for that is actually for fault tolerance. So for example, if one of the reduce tasks fails, we can launch a new copy of it and send it back all those records that were meant to it. So that's what this happens for. Okay. So we've seen the basic model. Let's talk about the fault tolerance. There's actually three types of faults that MapReduce handles. The easiest one is if one of these tasks is lost. And if that happens, the system is set up so you can just run a new copy of the task, maybe even on a different node, and it will still work. So for a map task, this is fine because it just needs to read in the input data, which was replicated to begin with, so it's still there. For a reduce task, because these map outputs are all on disk, we can go ahead and fetch them again and run the task on a different machine. Of course, if your task keeps failing, there may be a bug in your job, so the system isn't just going to keep doing this forever. It will eventually stop and just tell you the job has failed. One important thing to note here, though, is if you want to take advantage of this feature, your tasks should be deterministic. So every time you run them, they should give you the same result. So you have a consistent result at the end. And they should also not have side effects, because each task could be run multiple times. So if your task went and updated something in a database or something, you may do that twice, which would be bad. So this is something to be aware of when programming these jobs. Okay. The second type of fault is if a whole node goes away. So if a node goes away, there are two problems. You've lost all the tasks that were on it, but you've also lost the data that was on it. And in particular, there might be some of these map outputs on disk that are suddenly lost. And what MapReduce does in that case is for all the maps that were on the node, it reruns them on a different node. And it can actually spread them out across the cluster. So it can do this in parallel and catch up sort of much faster than having to redo all the work of that node in one place. And once you have that, you're in good shape and you can start going forward with the job again. Okay. And the third fault is an interesting one. Is everything is working except that some nodes are just very slow. So this is really bad because your job will go as slow as the slowest node if you just let this happen. And having this whole parallel cluster won't help you because you have one node in there that's holding everything up. This actually happens pretty often, especially in bigger clusters, just because you have all these nodes, they're flaky, and different things can go wrong on each node that will slow it down. And there are all kinds of stories about things that go wrong. You have a disk that's failing or things like that, and it just goes along very slowly. So it's important to do this right. And the solution here in MapReduce is that if a task is suspected of going too slowly, the system will actually launch a second copy of it too on a different node and let them race to the finish. So whichever one finishes first is the one that it uses. Again, it does this automatically for you. And of course, it requires your code to work if there are two copies of a task happening at the same time. So no side effects, deterministic, and so on. All these things have to be done. Okay. So just the high-level takeaway to get from all this is MapReduce gives you this very simplified programming model where you just write this map and reduce function. And because of that, it can do all these kinds of scheduling things for you underneath. And you don't need to worry about them yourself. So you don't need to worry about load balancing, putting stuff near the data, recovering from failures, and so on, as long as your job fits into this model. Yep. Yeah, that's a good question. It often is. If your reduce is doing something associative, like counting things or adding them up or whatever, then it can be exactly the same. Sometimes you'll want to count some things and then do something with the count at the end, and then you'll have a reduce that's maybe different from the combiner. So that's when you might do it differently. Yeah. Yeah, but usually in many jobs you will want to have a combiner and you can set the same one. Okay. Any other questions at this point? No. Cool. Okay, so that was MapReduce. We'll just go through some example applications to see how you could use this for stuff other than word count. So first one we'll have is search. This is probably even simpler than word count. We just have a big data set, and we want to find the lines that match some pattern, that contain some word or something. And you can do this with only maps. So in your map, you receive each line, and you just output it only if it matches the pattern. And then in your reduce, you can either use the identity function, which means just pass every record through and don't try to change it. Or in Hadoop, for example, you can just tell Hadoop, my job won't have a reducer. So just save the map outputs and use that. So that's search. That's a pretty simple one. Another one that you might want to do is sorting. So you want to sort some records by the key. And here you can actually do it without writing any code using a little trick. So in MapReduce, what happens is the reduce actually receives all its keys in sorted order. The framework guarantees that you get those, and this is just to make some types of jobs easier. So all you need to do then is make sure that each reduce is getting sort of a contiguous range of the keys. And you can do that by setting this thing called the partitioning function that determines which reduce task each key goes to. So in this example, we have these animal names here, and we set up one reduce task to receive names starting with A through M, and one to receive names starting with N through Z. Then, because they get sorted by the framework anyway, you can just use the identity reduce function, and you'll get out some sorted files. So this is just something you can do. Okay, inverted index. This is, again, something you might want to do with text processing. So you have a bunch of documents. Say each of your records has the file name as the key and the text as the value of that document. And you want, for each word, you want the list of files that contain that word in them. So this is a very, very simplified version of what you might do if you were Google and you were trying to do a web index. This is what you'd start off with. So how do you do this? So in your map function, you can take the text, find all the words, and output these intermediate records that have the word and the file name for that word. So these are going to be your intermediate records. In your combine, if a word happens many times in the same document, we don't need to send many copies of it. So we can just make those unique before sending them out. And then in the reduce, you get these word and file name records, and you can just output the inverted index entry in the right format for your list of values. So here, for example, we sort the file names. Okay. Here's a picture of what that might look like. So we have these two documents here, two plays, and we want to build an index. And for the first one, for example, we see that the words to, be, or, and not all happen in Hamlet. And in 12th night, we have some other words. And then at the end, they get combined into something that tells you, okay, be is in both 12th and Hamlet. Afraid is only in 12th, or is only in Hamlet, and so on. So this is your index. Okay. Another one, building up on that, say we wanted to find the most popular words in the set of documents. There's a couple of ways to do that, but the easiest way to do that is we start by running this inverted index job and getting something that looks like this. That tells us which files each word is in. And then we can just count up the sizes of those lists. and get some word comma count type of records, and then we can sort those records using the sort job that we looked at before. So this is one way you could do it. And this is, there are more efficient ways to do it if you think about it. So for example, we don't need to actually have the full index here. We don't need the list of files each word is in. We just need the number of files. So we can map these things to word one instead of word file, as we did in the word count job. And if we only cared about the top 100 words, we can actually sort of estimate what they are in advance using sampling, and then only count those. So we don't have to look through the whole data set. But the basic idea is you can chain these MapReduce jobs together to do more interesting things once you have these basic pieces. Okay. And the last thing I wanted to show, just a more mathematical example. Say you want to do an integration. You want to integrate something over a big range. So one way you can do it with MapReduce is just to split your range into smaller pieces and have each of the map tasks integrate over those small ranges. And then at the end, in the reduce, you sum up all those values to get the integral over the whole range. So this is just as a general rule, if you have a big sum to do or something like that, you can probably do it with MapReduce by following this pattern. Okay. So those were the examples. So now I'll talk a little bit about Hadoop and about these higher level languages, just so you can see more concretely what it would take to use one of these tools. So Hadoop itself is written in Java, and to use it, basically you just need Java on your machine. You need to download it, and you need to unzip it, and you need to set this one config variable that tells it where to find Java. So it's actually not too bad to set up on your own machine. You can read this quick start guide on the website if you want to do it. And this will let you run jobs on your own machine. If you want to set it up on a cluster, it's a little bit more involved, but again, it's not horrible, and there are scripts with it that let you do that. There are three ways to write jobs in Hadoop. You can use the Java API, which is sort of the native one for Hadoop. You can use this thing called Hadoop streaming that lets you write jobs in a scripting language like Python and gives them all their data through sort of standard input, so you don't need to do anything fancy to get the data. And there's this thing called pipes that lets you write jobs in C++. So just as an example, the word count job, I'll show the word count job in Java just to show you the pieces you have to do. I won't go into too much detail on this, though. The first thing you have to do is write your map and reduce. And you do this by having a Java class for each one. So say your map class, which implements Hadoop's mapper interface. And it has a map function. And basically, the function is given a key, a value, and this thing called output collector where it can write its output. And then it just has to output all the values you want to get from that map. So in this one, we split the line into tokens, and we collect each token. And this text class is sort of Hadoop's version of string. It's a little bit more efficient, and so that's why you have to use this instead of string. Okay, so that's the map. This is a lot like the pseudocode I showed earlier. Reduce class is very similar. You basically implement this reduce function, and you get a key and a list of values, and you have to output whatever you want to do with that. And here we just add them up, as we had in the code before. And the last thing you write is this driver program that actually sets up a job and submits it to the cluster. Just the way that works is you create this configuration object. You tell it some stuff like which map class, which combiner, which reducer, and so on. And then you say run the job. And that's basically how it works. Okay. Word count in Python. So if you use Hadoop streaming instead of Java, the code is actually a lot smaller because you don't have to write these separate classes. In Hadoop streaming, your map is just a script that is supposed to read its input from standard in. And same thing with your reduce. So you can just write these scripts and set up the right commands to launch them, and your job is running. And another nice thing about this is if you want to test these separately, you can just run each script by itself and start typing in stuff. And so it's easy to do. Okay. So that was that. Let's see. Yeah, I still have a bunch of time. Okay, so I'll talk now about the Spig and Hive. And again, let me know if you have questions. I think there will be time at the end for questions too. Okay. So what we've seen so far is we had all these examples of parallel jobs you can write with MapReduce. And it turns out there are a lot of different things you can do. But in many of them, you have to write a bunch of separate MapReduce jobs and chain them together. And each one does one operation. So for example, in the popular words one, we had to first build the inverted index and then pull out the words and then sort them and so on. So it would be nice if you didn't have to just write a whole bunch of Java classes or Python scripts, but you could just say or use this higher level operation directly. And this is what Pig and Hive try to do. Okay. So we'll talk about Pig first. This is a project that started at Yahoo Research and is now used in production by Yahoo. It's been in production for a long time, actually. And it runs a lot of Yahoo's jobs. And the idea of Pig is to have sort of this higher level scripting language on top of MapReduce that lets you express some common operations. It has the main thing that gives you is these SQL operations. If you've ever used a SQL database, things like group bys, joins, select, and so on. So you can write something that looks a little bit like SQL, but gets compiled into MapReduce jobs and runs on these clusters. You can also call Java functions from it pretty easily. So you can combine these operations with your own stuff. Okay, I'll just show an example of a Pig application you might want to do. So here we have two data sets. One is about users. So for each user, we have some information like their age and their user ID and so on. And one is about page views. And this just says, oh, user 17 watched this page at this time. And given these data sets, we want to find the 5 pages that are most visited by sort of users between 18 and 25. So this is the kind of thing you might do as an analytics person at Yahoo, for example. And so here on the right, we have sort of the pipeline that we'll want to happen in this job. Oh, sorry. Okay. So we'll take the users. We'll actually pull out only the ones of the age range we're interested in. Then we'll take the pages, and then we'll do a join, which means sort of for each page record, bring in the data about that user. So if we say user 17 looked at CNN.com, we also want to bring in user 17's age, for example, or name or something like that. So this gives us this data set with user and page views grouped together. The reason we're doing this is to get sort of the unique users that viewed each page in the same location. Then we can group these by URL. So now we have a list of unique users for each URL. And we can count up the clicks. And then we can sort them using the sort job and take the top 5. So this is kind of a long pipeline that we want to do. You can write the job in Java. This is someone else wrote this, but you can see, it's a bunch of code, but it does actually do it. And you can also write the job in Pig, and this is what it looks like in Pig. So what we see here is Pig has these operations like load, filter, group, join, and so on that capture these building blocks. You write this one script where you say which steps you're going to do, and you just execute it, and it takes care of launching all these MapReduce jobs for you. I'm not going to go into too much detail on the Pig syntax. It's just meant to give you an idea of what it looks like. Okay. And the nice thing about it is, all these lines we wrote where we do different things are mapping very nicely to the pipeline we wanted to set up. And that's, Pig is designed to do that for you. The other interesting thing Pig does is that it tries to optimize the pipeline into the smallest number of MapReduce jobs and to put together things that can be changed. So, for example, if a map function can do both some of the previous step and some of the next step, it puts them together. So here it sets up these 3 jobs actually. So it might run faster than if you wrote it by hand as well. Okay. A little bit about Hive. Hive is a similar project that was developed at Facebook, and it has a few differences that make it interesting. So you saw Pig was sort of the scripting language that looked a little bit like SQL. Hive tries to be very close to a database and just to be built on top of Hadoop. So the main differences between Hive and Pig are that Hive's language looks exactly like SQL. It's a subset of it, but if you've used a database, then you can use Hive and express your jobs in it. And also that Hive has a notion of tables and schemas and so on. So in addition to letting you express a job, it also takes care of the organization of your data. And this is kind of nice because as you start using Pig a lot, you'll see that you have to keep telling it, oh, this data is in this format, this other data is in this other format, and so on. And Hive tries to do that for you. And it has a bunch of neat features which you might care about if you have really big data sets. It has sampling. It does some optimization. It has this partitioning of tables, which is useful. And so on. It's also very easy to call Python from Hive. So those are some of its advantages. Okay. And so the last thing I just wanted to show is how you might submit this job to a cloud environment and Amazon Elastic MapReduce specifically. So as I said, if you want to run Hadoop locally, that's pretty easy. And the next easiest thing after that, actually, if you want to run your job in parallel, is probably the Elastic MapReduce, just because they made it very, very smooth. So here's a bit about the service. So basically, Elastic MapReduce gives you this web page where you can submit a job. And it launches a cluster on EC2 for you. It monitors it. It tells you if stuff goes wrong. And then it shuts it down at the end. Your data has to be in Amazon Storage Service S3 to be able to use this. So you have to upload your data there, which kind of makes sense. It has to be in the cloud. Here's what it looks like. So you give it a name for your job, and it supports all these different ways of writing jobs. So you can use Hadoop streaming, the Python one we talked about. You can upload a jar file containing your compiled Java program. You can give it a Pig script. I think you can actually use Hive now. This is an older picture of it. And so that's how you set it up. After you set it up, you actually tell it where the input is, and you tell it how many machines to use and which size of machine. And then you hit launch, and then it tells you, okay, here are all your jobs, and this is what each of them is doing. So if you just want to run MapReduce jobs in parallel, this is a pretty straightforward way to do it. We've actually used it in a couple of courses at Berkeley already to have some undergrad students write assignments that run on EC2. Okay, and that's really all I wanted to say about it. Okay, so some conclusions then. So the MapReduce, the key idea behind it is we'll give you this high-level programming model that's very simple, and so that you don't have to worry about work distribution, scheduling, failures, load balancing, all these kinds of issues. The system will hopefully just do them for you. The motivations and the philosophy behind it are really to make it very scalable and to make it very cheap and self-managing. And it's been pretty successful at both of those. Depending on your applications, there are also these higher level tools such as Hive and Pig, which make it easy to express these data crunching sort of database query type of jobs. The main takeaway really is because this is a very stylized programming model, it may not be the right thing for all applications. But for those applications where it is the right thing or where you can somehow think about how to fit your job into map and reduce functions, it's a great thing to try first because it might just sort of work out of the box for you and you don't have to worry about doing something more complicated. That's it from me. The last thing I have here is some links to tutorials and documentation about these systems. And if you want the tutorial to start with, I think is really these video tutorials from this company called Cloudera, where they have a whole set of mini lectures where they talk about using MapReduce, using Hadoop, and so on. And they're available for free online. Okay, that's it. Thanks. Any questions? Yeah.
So when you presented the structure of the Hadoop cluster, when you presented the structure of the Hadoop cluster, you mentioned like the data nodes. Mm-hmm. Are these only data nodes, or just they doing processing and having data at the same time? This is the first question. Okay. And the second question, you mentioned about if one task is taking so long in one machine, then mm-hmm. the Hadoop manager will start to fire a duplicate of this task in another machine. So mm-hmm. my question is, what is the power efficiency? Because you are trying to fire more one than task, and then you're consuming more power for doing the same thing. And sometimes the mm-hmm. task itself, it's so long, so it should wait for it.
Right.
And third one, that's too long. Okay. Third one is like, okay, you have master node. So what's the dependency? What if this master node fails?
Yeah. Okay, so these are all very good questions. Okay, so let's start with the first one. You asked about the data node. Does it have only data, or do you also run computations on it? So you definitely run computations on it. The reason it's called data node is in that picture was just because the Hadoop file system and Hadoop MapReduce are two different software systems. So in HDFS land, it's called the data node because that's what it does. But on the same node, there's also a MapReduce daemon running that runs stuff. Second question was about the speculative execution of slow tasks. Why do we launch a second copy of it? So yeah, this is an interesting question. So if you depending on what you care about, whether it's throughput, response time, cost, and so on, there may be different reasons to do it. So if you only cared about throughput and didn't care about how long it takes to get your answer at all, just how many jobs per second you do, then you may not want to enable this feature. You may want to just run tasks. But you still have this risk, though, of one node being so slow that all the jobs just get backed up on it. And this can be bad for, it can actually be bad because you run out of disk space because all the intermediate results are filling it up. It can be bad because reduced tasks are waiting for a slow map task to finish and hogging nodes or whatever. So it's not a great thing, but you can turn it down if you don't care so much about response time. If you do care about response time, of course, it lets the job get you an answer faster. And it is a tunable thing, and there's probably no single best answer for it, but there are different ways you can set it to have it be more aggressive or less aggressive. Okay, and third question was master fault tolerance, right? Yeah, so the master nodes in Hadoop aren't fault tolerant now. They are, however, so if you lose your master node for the file system, for example, you haven't just lost all your data because it can replicate the data. It can log, what it's doing on several nodes at a time. That's how you deal with that. But if it goes down, then yeah, the file system is unavailable until you restart it again on a different machine. So the reasoning for this is just to make the system simpler at this point. It's probably not going to be this way forever. But one like one interesting statistical argument about why they do this is in a given job run, it's much more likely that one of your worker nodes will fail than that the master node will fail, because you have 1,000 worker nodes and one master. So it's, even though it's likely that some machine will fail, it's very unlikely that that will actually be the master. That's why they sort of get away with this. Yeah. Okay. Other questions? Yeah.
So this question is about, well, I mean, Hadoop existed before, and they're trying to use scientific applications with it.
Yeah.
Are there people using it now, or it's still looking for ways to do it? Interpreters from API.
Oh, so migrating from MPI to Hadoop isn't. It will probably require rewriting your application because they're very different models. MPI is this pretty low-level thing where you send messages. Hadoop is this super high-level thing where you never have to know where you are in the network and you just run. Hadoop is used by a bunch of companies now, not just web companies, but also things like Bank of America or Visa or things like that. And it's typically used for these data-intensive applications. That's its biggest selling point, is that it knows what to do about data. It's also okay if you have, say, a compute-intensive application that fits nicely into the model, then it's probably easier to write it on Hadoop than on MPI. It may not perform as well, though, or, it may not be great for that. So yeah, so it is used fairly widely, I guess, as far as these kinds of software projects go. But it's not going to replace MPI, and it's not even optimized for some of the jobs that MPI is really good at. Yeah. Okay. Oh.
Yeah, I have a question that's kind of along those lines. I basically just want to ask about two things that are basically all of what I do. One is I'm doing things that involve a few iterations, and it seems like that might be a bad match for the MapReduce model because of all the overhead, because it went to disk at each iteration.
Yeah.
And the other thing, maybe this is a better question to ask offline, is do you know of people doing things where they're solving like large linear algebra problems? Again, it seems like it might be a bad match.
Okay. Okay. So the iterations one, you're absolutely right that if you're doing many small iterations, Hadoop isn't really optimized for that. So it's optimized for batch processing. It's not optimized for, I have a job that will take 2 seconds. Can you do it in 2 seconds? Interestingly, this is kind of off topic, but we have a research project at Berkeley that I'm working on that tries to do iterative jobs better and to give you the same ease of programming and fault tolerance properties that MapReduce does. So if you want, you can shoot me an email or catch me after the talk or something like that about that. And for linear algebra, I think basically for both of these, people have used Hadoop in cases where the data is so big that each iteration or just the whole job will take many minutes, and then the overhead of starting up and shutting down and so on doesn't matter much. But for smaller jobs, shorter jobs, I don't think they really use Hadoop. I think there are many MPI libraries that really shine for those. Yeah. Okay, I think that's it, so thanks.